Consider any group G, and then a set X. In this program, we're concerned with the situation where elements of G act on points in the set X. Given an element G in G, and a point X in X, then G acting on X takes X to a point GX, which is also a point in the set X. This is the idea of a group action. Each element of the group G acts on each point of the set X. Well, that's an abstract picture of what we're going to be looking at today. Here's what you've just seen. Notice how I've represented the action of the group element G by this G in the box. Here's another element H of our group. And here's the product HG, which is also an element of the group. Let's suppose that HG takes X to this point. Now, the action of a group should in some way mirror the structure of the group. So HG should combine the action of H with that of G. That is, the action of H on GX should give us the same point. And that leads us to the first of our two axioms. For every point X in X, the action HG on X equals the action of H on GX. There's another axiom we need. We'll look back at our group and at the identity element in particular. You see, the identity element E of our group is a rather special kind of element. It's the product of any element G with its inverse. Now, the inverse of G should undo the effect of G and send GX back to X. So it follows that the identity element E should leave X fixed. So this becomes our second axiom. For each point X in X, EX equals X. Now that I've established what's meant by a group action, I'm in a position to take an example of a group G acting on a set. Let's look at this example. The group G will be the real numbers under addition. The set X will be the plane R2. So what we've got to do is to specify an action of G on X. The set X is the plane R2, and we want to consider a point in that set. A point we've called X. Now we'll consider an element G of the group. Remember, the group is the real numbers under addition. We define its action to be a rotation by G radians. In this case, G is 2 pi on 3, and the point to which X is moved is GX. The question we must ask then is this really a group action? Does it satisfy the axioms? Well, what does the first axiom say? Remember, our group operation is plus. So two elements of the group H and G added together to act on X should take X to the same point as H acting on GX. Well, how does this work for our example? Another element takes GX to here. This is a further rotation by H radians. This is the action H on GX. Now, we could have got to that point directly from X. This is the rotation through G, followed by the rotation through H. That's the same as the rotation through H plus G. So H plus G acting on X is the same as H acting on GX. So the first axiom for a group action is satisfied. Now for the second axiom. 0 is the identity of our group, and clearly a rotation by 0 radians will leave X where it is. So both these axioms for a group action are satisfied. We now know that we've defined a group action, the group R+, acting on the set R2. So what? It's no use just checking axioms and finding that we have a group action unless we can do something more with it. So I'm now going to use this example to illustrate some general properties of group actions. One element of the group G will take X to here. Another to here. And another one will take it to here. And so on. And taking all the real numbers, we get all the points on the circle. This set is called the orbit of X. In general, the orbit of the point X is the set of points Gx for all elements of the group G. Another element from the set would have a different orbit. If we were to carry on drawing these orbits, we would eventually cover the whole plane with concentric circles. The origin is rather special. The orbit consists of a single point, the origin itself. Every group element leaves that point fixed. Now we ask, which group elements leave the point X fixed? We already know the identity element 0 will leave X where it is. So will 2 pi, a complete revolution. Four pi will also fix X. So will minus 2 pi. The set of integer multiples of 2 pi then leaves X fixed. We call this the stabilizer of X. In general terms, the stabilizer of X is the set of all elements in the group G such that the action G on X will leave X fixed. That example then should give you some idea what's meant by the orbit and stabilizer of a point. Now here's the definition you've just seen of the orbit of X. You'll notice that it's written as a subset of X. The stabilizer, on the other hand, is part of the group G. In fact, it's a subgroup of G. There's a proof of this in the text. It's an important property of the stabilizer, and we'll make use of it later in the program. So far then, we've looked at the axioms for a group action, and then we've introduced two sets for each point X. This subset, the orbit of X, and this subgroup, the stabilizer of X. Now, what is of particular interest to us is the connection between them.
Well, that was an infinite group acting on an infinite set. We'll be seeing more about the orbits and stabilizers for that particular example later. But to examine the connection that David was talking about, I'm going to look at a finite group. The group is the dihedral group of order 8, the symmetry group of the square. Let me just remind you what the 8 elements are. First, of course, there's the identity element. That's the element that leaves the square where it is. Then there are the rotations. Through a quarter of a turn, through half a turn, and finally through 3/4 of a turn. These 4 elements then, including the identity, form the rotations. Then there's a set of 4 reflections about each of the symmetry axes. This symmetry, for example, reflects points on one side of the diagonal to the other side, and vice versa. and similarly for the other reflections. These 8 elements in all, then, form the symmetry group of the square. Now, we know that symmetries of the square are in fact transformations of the whole square. So we can think of the group as acting on the set X of all points in the square. And the action of a symmetry on a point, of course, is what happens to the point when we perform the symmetry. And it's obvious then that the axioms for a group action will hold. You can check that yourself after the program. But what I'm going to do is examine the orbits and stabilizers of individual points in this set X. And I'll start with this point on a diagonal. I'll apply all of the group elements to the point, and that will give me the orbit. I'll start with the identity. The identity applied to the point leaves it where it is. I'm going to summarize my results here. The identity acting on the point leaves it fixed. Now, there are also 3 rotations in the group. So I'll take this quarter turn and the half turn and the 3/4 turn. The quarter turn acting on the point takes it to here. The half turn takes it to here, and the 3/4 of a turn takes it to here. So the 4 rotations acting on the point give me this set of 4 points. There are also 4 reflections in the group. This reflection, this one, and this one. This reflection leaves the point fixed. This reflection brings it across to here. This reflection, that moves it down here. And finally, this reflection takes the point to here. So that gives me these 4 points in the orbit. And you'll notice that the reflections and the rotations give me the same set of 4 points. So, even though there are 8 group elements acting, the orbit consists of only 4 points, each one coming from 1 rotation and 1 reflection. Right, that's got the orbit. Now what about the stabilizer? Which group elements applied to this point leave it where it is? Well, the identity always has to be in the stabilizer, and this reflection we saw doesn't move the point. And every other group element does move the point. So this set contains all the elements of the stabilizer. I'm going to look at some other points in this square. If I were to take this point on another symmetry axis and work through, I'd find again that rotations and reflections give the same set of points in the orbit, and again the stabilizer consists of just 2 elements. Well, those were points on symmetry axes. This point, not on any symmetry axis, a general point, is a bit more interesting. I've got a summary of how the group acts on the point over here. You see, I've shown all the group elements acting on the point. Now, the 4 rotations acting on the point give me these 4 points, and that's this set. And then the 4 reflections acting on the point give me these 4 points, and that's this set. And you can see that these 2 sets are not the same. So the complete orbit consists of these 8 points. And all of the group elements, except the identity, move the point, and so its stabilizer is just the identity. To complete the picture, there's one more point we should look at. That's this point in the center of the square. Now, every group element acting on that leaves it where it is, so the orbit consists of a single point, and the stabilizer is the whole group, G. And you may have noticed that points with more complicated orbits have smaller stabilizers, and vice versa. In fact, in this case, the product of the number of points in the orbit and the order of the stabilizer is always equal to the order of the group. You see here the order of the group is 8, and we have 4 times 2, again 4 times 2, 8 times 1, and 1 times 8. This is not just coincidence, but why? I'm going to look at a single case. This point, the one we started with. Here are the 4 points in its orbit, and I'm going to find which sets of group elements move the point to these 4 positions. First, which elements leave it where it is? Well, of course, it's this one and this one, the elements of the stabilizer. Now, how can we get to this point using an element from the right-hand board? Well, we see that either of these 2 elements bring us to here. What about here? Well, this time, it's these 2 elements. Finally, to here, we use these 2 elements. Well, we've got the whole group here in these 4 sets. And what we've done is to classify the elements of the group according to where they move the point. And this first set is the stabilizer, and these other 3 are cosets of the stabilizer. Well, let's see why that happens. We get a coset by multiplying the stabilizer by some particular element. For example, this rotation. If we do this, we'll find we get this set here. We don't have to work it out in detail, because if we multiply this rotation by an element of the stabilizer, that means first perform something in the stabilizer and then perform this rotation. Now, what does something like that do to the point? Well, first we perform something in the stabilizer, and that doesn't move the point because it's in the stabilizer. And then we perform this rotation, and that moves the point down to this position here. So, anything of the form this rotation multiplied by something in the stabilizer moves the point to here, the same place. So, cosets of the stabilizer have the property that all of their elements move the point to the same place. And that's true even of this set, which is the stabilizer itself. That is a coset. And that's an important result. There's a correspondence between the cosets of the stabilizer and the points in the orbit. In fact, we can generalize this idea to give a theorem, the orbit stabilizer theorem. There's a bijection between the orbit of X and the set of all cosets of the stabilizer of X. Now, how does that tie up with what we had over here? Well, remember, the stabilizer is a subgroup. We said that before. And we saw how the cosets of the stabilizer partition the group. And by Lagrange's theorem, the order of the group divided by the order of the subgroup gives the number of cosets. And in this case, we have 8, that's the group order, divided by 2, the stabilizer subgroup order, which gives 4 cosets, and there are 4 points in the orbit. So that agrees with what the orbit stabilizer theorem tells us. And in general, if a finite group acts on a set, then the number of points in any orbit must divide the order of the group. That's a consequence of the orbit stabilizer theorem applied to a finite group.
Right, all that was demonstrated for a finite group, although the proof in the text works for any group. But now let's take another look at the infinite group we saw earlier and see how the orbit stabilizer theorem applies here. Remember what to look for: a one-to-one correspondence between the points in the orbit and the cosets of the stabilizer. Here's a point X in R2. Its orbit, we know, is this circle. Now remember, the group acting was the real numbers under addition, and we represent it here by this straight line. The stabilizer of the point X we saw is the set of all integer multiples of 2 pi. Now the orbit stabilizer theorem tells us there is a one-to-one correspondence between points in the orbit and cosets of the stabilizer. Well, the integer multiples of 2 pi themselves form a coset, So what do they correspond to? Well, the identity leaves x fixed. So does 2 pi. So does 4 pi. And so on. You'd expect this, since this coset is just the stabilizer itself. Now let's take another coset of the stabilizer, say this one. These are some of the elements. Can you see there's a correspondence between the coset and one point in the orbit? Conversely, we could look at any other point in the orbit. Can you now see that for that point in the orbit, there is a corresponding coset of the stabilizer? Of course, that should remind you how we measure angles. Here the orbit stabilizer theorem gives the relation between points on the circle and the real numbers modulo 2 pi. Well, that was for an infinite group. The other example we've looked at today was a finite group, the dihedral group of order 8, acting by symmetries of a square. And here the orbit stabilizer theorem told us that the size of an orbit multiplied by the order of the stabilizer had to be the order of the group. Well, the orbit stabilizer theorem then is a general result about group actions, and it tells us a number of different things depending on which group action we apply it to.
Here's another group action for you to look at. It's something for you to do after the program. But to get you started, I'll just give you some idea how it will go. You take a general group G, and the set will be G again, and the action is defined this way, that's conjugation. You'll have to check the axioms in the usual way. Then you'll be asked to show that the orbit of a point is equal to its conjugacy class. Now, the size of any orbit divides the order of the group, so the size of a conjugacy class must divide the order of the group. That's a consequence of the orbit stabilizer theorem. Well, that's the gist of it. The details I'll leave to you.